Okay, System Devices 1, Week 7 review, what you should know by the end of the week. So in this week's lecture, we look at how we can use our instructions to actually implement something in the real world that does something useful. What we're going to look at, as always, when you have any new machine, is printing Hello World to the screen. So for the simple CPU, you've got two choices. You can either print it to an LCD display, or you can print it down a serial cable and display it on a terminal running on a PC. And we're going to look at both cases. So for printing Hello World to the screen on the LCD display, we're going to build a software-defined parallel port to allow us to talk to that LCD module across a 4-bit bus. So we're going to build that in ISC, and then we can write a program to actually control that software-defined parallel port. Now in the lecture I go through this one in detail. Everyone should be able to understand what's going on with this program. There's a little bit of bit manipulation going on. We're shifting some bits around, so the values are changing, but basically this is a cut and paste solution based around a standard block of code. So fingers crossed, touch wood, everyone should understand that one and be good to go on that one. We then move on to the serial port implementation. Now this one here is designed to be horrible. I make no apologies for that one. This is the ultimate test of whether you understand what's actually happening inside the machine. So this is more of a challenge. And do take the time to go through this one and see if you can understand what's going on in this code, because it is complex. If on the other hand, when you read through it and you think this one is easy, then well done. You have achieved the desired level of assembly language program that I was looking for. Finally, we finish off this week's lecture by looking at adding some application-specific hardware. So we're looking at a communication device, we're looking at our serial port, our UART, our Universal Asynchronous Receiver Transmitter Unit, and how that can be mapped into the processor's address space and how it greatly simplifies our program to print Hello World to screen. So in summary, do make sure you go through those assembly language examples. So in the private study exercise, we saw how we could do multiply using repeated adds. We'll also be looking at shift and add techniques in the weekly exercise sheets, another way of doing multiplication. This week we've looked at the Hello World via the LCD display. Again, I should have said that should be easy to understand. If it's not, do give me a shout, drop me an email, happy to chat. Finally, the Hello World via the serial port. Yes, that is a difficult example to understand. And we will be covering that one again in next week's lab. So hopefully with the combination of this week's lecture and next week's lab, you'll see how that program does work if you don't understand it at the moment. Okay, and then we had this week's lab, and as I said in the announcement, this is a make or break lab. So this really does test if you understand what's going on inside our processor, how it's actually implementing those instructions. So again, this is based on CPU Sim, and we'll be adding our absolute address mode instructions. And the first point I'd like to highlight here is, what do you need to know when you look at one of our assembly language programs? And the key thing is you have to know the machine level instructions. So when you look at this program here, we've got a load, add, and a store. What do these values actually mean? So what are these operands? And obviously it all depends on the addressing mode. So for the load and store, obviously these are addresses. So I'll be reading and writing the data stored at address 3 out in memory. And I will be adding the immediate value, the constant one, to that value that will be stored in the accumulator. So make sure you're happy about the instructions. Make sure when you look at a program, you can identify obviously what the opcode is doing functionally and what the operand is specifying. Now for some processors that would be a bit of a nightmare. You'd have many hundreds of instructions, but the simple CPU, you've got about 11 instructions, so you should know those off by heart by now. Okay, so we're going to add our load and store instructions to our simulator. So again, fixed length instruction format, all instructions are 16 bits long, so we've got a 4-bit opcode and a 8-bit operand value. And again, just to highlight that again, this now specifies the address at which our data will be stored out in external memory. To make our program a little bit more easy to understand, we can add some assembler directives. So we have the equals and the .data directives you can see here. In addition to that, we can add symbolic labels for instructions within the program and for our variables. And also that makes your code a lot more easy to write. You don't have to kind of manually maintain or update the instructions with the absolute address, in the previous example, 3, as that can be a bit of a pain as your program grows and shrinks as you add and remove instructions. So in this example here, obviously what happens is the assembler will read through this program in its first pass. It will identify the address of where these symbolic labels are within the program, because it knows that each machine level instruction takes up one memory location. It knows the process starts at address 0, and then so that's going to be 1, 2. So our data A here will be at address 3, same as the previous example. So in your program, sometimes your data is uninitialized, and sometimes you want to initialize it to a value. If you want to initialize it to a starting value, then you can tell the assembler that by using an assembler directive, the .data command. So remember, this is not an instruction that will be executed by the program. It's a command to the assembler. So you're telling the assembler that you want to reserve some space for a variable. You're reserving one memory location and you will assign it that value, the value 0. In this example here, actually, in reality, that would not be required because the simulator resets its memory to all zeros on power up. Just to make sure, obviously in the real world, you can't guarantee that a memory location has been reset to 0. It'll just probably contain random rubbish. So it's always good practice to reset your variables to a known initial state. Again, to make your program a little bit more readable, rather than having random numbers within the program, again, you can assign those a symbolic representation. In this case here, the label offset. So again, within your program, this is not an instruction. This will not appear in your program. It is, again, a command to the assembler telling it that if it sees the string offset, that it can replace it with the value 1. So in this lab, there's a series of tests to make sure you understand what's going on. And here's your first one. So knowing that the .data directive will initialize a memory location with this value, what does this code do? So to answer that question, let's run a slightly modified version of the previous program. So you can see our previous program here, and I've added a new data value at the bottom there. So if I was to reset the machine to clear memory and then assemble and load, you can see a particular bit pattern loaded into memory. And if you compare back to the lab script, obviously that is the same bit pattern. So in the previous example where we defined the .data, we're actually defining the machine code that will be loaded into memory. And if we were to execute that program, as always, and if we step through at the microinstruction level, we'll see we'll execute our standard fetch. I'd always recommend placing the displays in hexadecimal. So that allows you to see the opcode field, which is obviously the top nibble, and the operand field, which is the lower 2 nibbles, your 8-bit value. If you use a decimal representation, obviously it's not clear what that particular value is representing as an instruction, so always use hexadecimal. So yeah, we've now done our fetch. We've fetched in our value into the instruction register. Obviously that will now be decoded. Then we'll jump to the micro instructions associated with that particular machine level instruction. So the machine will look at the opcode value, go, that's the value 4, so therefore I will go to the micro instructions associated with the load instruction. Then I drive the address that is in the instruction register, those lower 8 bits, onto the address bus. And then I can read memory and transfer that value into the accumulator. So again, stepping through at the micro instruction level, we'll update our address bus to the value 3, because obviously that's where my data is stored out in memory. I will then read that memory location and transfer the value into the accumulator. Now the key point to note there is that obviously memory locations are 16 bits wide, but our internal data register is only 8 bits, so I cannot fit all 16 into that register. So I will only read the lower byte. And that's how the simple CPU is wired up. It doesn't use byte addressable memory, which would be obviously a far superior way of doing things. It keeps it nice and simple, and we just use that lower byte. So that means that we will never actually read or write to that higher byte. That value is just not used, so it's not very efficient, but it's nice and simple. So we load that value in, and obviously that is the end of our load instruction. We then go back to our standard fetch decode cycle. So we fetch in the next instruction, which is obviously at address 1, and we'll load that into the instruction register, and then we'll increment the program counter to point to our next instruction once we've finished executing the add instruction in this case. So again, looks at the opcode, it's opcode 1, so we'll add 1 to the accumulator, so that will run the micro instructions that do that one, so we'll add 1 to our accumulator and update that value. Again, now we've come to the end of that machine level instruction, so we'll fetch the instruction addressed by the program counter, in this case address 2, so that will load in our store instruction into the instruction register. We'll increment the program counter ready for the next instruction fetch. Then we will decode that machine level instruction in the instruction register. We'll look at its opcode value, so value 5, so we know it's doing a store instruction. So we'll jump to the micro instructions associated with the store. We'll update our address bus to the address stored within that instruction. So again, it's the address 3, because that's where we're writing it back to. And then we'll perform the write. We'll transfer the contents of the accumulator out to memory at that address. And we'll see now the data at address 3 being updated. Now, because we can only write the low byte, we'll only actually write the value 35 to that memory location. The top byte will be 0, because that's how it's set up in CPU Sim. In reality, that will be hardware dependent, and if you look at the ISC schematic for the simple CPU, we see we do something slightly different. And we looked at that when we looked at our new store instruction when we did our wheeler jump. So the store instruction, which had 2 operands. It had an immediate value, that 4-bit value, which we normally don't use, the unused field, and as always, the address where I'll be writing to. Okay, back to our lab script. So the second waypoint within the lab script. So our second make or break test. Do you understand what this program does? Again, it's designed to be a little bit horrible, but do ever think about what it is actually doing. What is the label start representing? What will I load into the accumulator after this load instruction is executed? What will I write back, and where will I write it? And what will happen if I jump to the start label? So again, to answer that question, let's see our program running in CPU Sim. So here's my program. If I reset everything and assemble and load, you'll see the machine code being loaded into memory. So in this program, we have our final set of instructions. So we have our unconditional jump, so a jump that always will happen. So again, the symbolic label start is the address of the start of our program in this particular case. Again, that name could be anything. I'll just use start to indicate it is the start. And obviously for the simple CPU, that will be address 0, because on reset, the program counter is reset to the value 0. So the first instruction I fetch is at address 0. So knowing that the label start represents the address or value 0, now start to think about what is going to happen within that program. So again, look in memory here, you can see that the top nibble here is a 4, indicating it's a load instruction, and the lower byte contains the address 0. Again, you can see it with the jump instruction. Most significant nibble is a 8, indicating it's an unconditional jump, and I will be jumping to address 0. Store instruction, again, opcode 5, again I'll be writing to address 0, and address 0, remember, is where I'm storing my load instruction. So if we were to single step through this program, so we'll step through at the machine level instruction, so this button here. So after we've executed the first instruction, nothing really changes. Obviously, the accumulator will be updated with the value 0, because obviously it will load into memory the low byte at address 0, and the low byte at address 0 is the value 0. Then I perform the add instruction, so I'll add 1 to the accumulator, and now I will store that out to memory. Now I will store the result 1 out to memory at address 0, overwriting the load instruction. And as we saw in the previous example, when we had that value 1, 2, 3, 4, when I write that value out, the high byte will be 0'd. So now that bit pattern has been changed. The load instruction has disappeared, such that when I execute the jump instruction, I will jump back and now execute the bit pattern associated with 0001. And again, if you know your opcode values, which you should do now, you'll recognize that the opcode for 0 is the move instruction. So you can see here I've executed the jump, so the program counter is now pointing to address 0. So if I now step through at the micro instruction level, again I will fetch the instruction at address 0, which I have modified, and when I decode it, it will decode it as a move instruction. Now I will move the value in this instruction into the accumulator, so now the value 1. And again the program continues. So now if I step through at the machine level instruction again, have a look at what's going on at address 0. You can see that it is counting. And again, if you go back and look at the exercise sheet and you had that programming problem, how do I reduce the number of instructions down to just 4 memory locations? This is how you do it. We can use the immediate operand field within an instruction to store data. And again, just to emphasize that one, I'm not saying that self-modifying code is a good programming technique, but it does raise those questions about what is an instruction and what is data. And the line blurs, so you can do some really interesting things when you start to misuse your processor. Okay, back to the lab script. So in the lab, we then looked at how we could translate the high-level pseudocode representations of our while loops and our for loops and our if-then-else trees into assembly language. And so some examples there to look through. So do check those out. Make sure you're happy what's going on with those. Then we started to think about what are the limitations of my current instruction set. So can I implement all the programming structures that I want to implement? And the answer is no. So if you tried to implement this for loop, you'd run into a problem. How do I incrementally read through an array stored in memory? So as this kind of syntax is representing. And the problem is we do not have an addressing mode that will allow us to do that. If you look at our load instruction, it's an absolute load instruction. You can only read in the value specified in the instruction. You can't change that load address. You could have multiple loads that loaded particular absolute addresses, but then you couldn't use those within that for loop. You just have a basic block of code, a sequence of instructions, rather than a repeated block of code. So as always in the Simple CPU version 1a, if you've got a problem, we can solve it with self-modifying code. So we could define our new store instruction, our store instruction that had 2 operands. It had an immediate value stored in the not used field and our absolute address that we obviously were writing to. So we created that new store instruction, as you can see here, and then we could execute that one to scan through an array stored out in memory. And in CPU Sim, that's how you represent that one. So again, the .data assembler directive, we are reserving space for 4 data values, and they are stored in an array of 4 elements. So as we go around the loop, I want to read in the 1, then the 2, then the 3, and then the 4. So do have a look through this program, make sure you're happy about how it works. So okay, let's see how we'll implement that loop in CPU Sim. So here we have the program that will do that one. So here we have our data stored out in memory. Here we have the index that I'll use to index that array. Here we have the variable m, which I'll use to calculate if I've reached the end of the array, and t is my running accumulation of adding the values up within that array. So I should add up 1 plus 2 plus 3 plus 4. So to start with, let's reset everything and assemble and load. So now we have the machine code loaded into memory. So we can see down the bottom here we have our array. So the first element of the array A is at address 12. And then we've got 1, 2, 3, and 4. And obviously then we have the variable for I, M, and T. And obviously they're initialized to 0 at the moment. So again, things to spot. You can see we're using the symbolic labels for our variables within our code to make it a bit more readable. So the first instruction here is to test to see what's going on. What does that instruction do? So move A. Remember, the move instruction is an immediate instruction. It does not read memory, so it will not read the data stored at address A. Here, A represents the address of variable A, not its data. So what it will do is it will move the address of variable A into the accumulator. And you can see that again if you look at the machine code. So again, top nibble is 0, so it's a move. The lower byte is the value 12. And remember, the value 12 is the address of the first element of that array. So the value 1 in this case here. So if I was now to execute at machine level instruction, the first instruction will load 12 into the accumulator. I will then store that out to a variable I. So if I step through that one, you will see, there we go, there's I updated to the value 12. I will also make a copy of that one out to variable M with the next store instruction. So there we go, there's M updated. I will then zero my running total, so I'll zero the accumulator and store that one out to the variable T. And obviously that's got nothing in it at the moment. Now here's our problem. So in our main loop, so this is our for loop here, we want to read through each of those elements in that array, but I can only specify in the load instruction one absolute address, the starting address of variable A. At the moment I do not have a load instruction where I can change that address during runtime. So we'll see in later versions of the Simple CPU, version 1D, we add a new addressing mode, the register indirect addressing mode, which will allow us to do that. But at the moment we can't, we haven't got that facility. So as previously stated, in Simple CPU version 1 land, we use self-modifying codes. So let's continue to run this program and see what happens. So the first load instruction there, when I run it, it will read in the first element, so I read in the value 1. I will then add to that my running total, so at the moment that is 0, so nothing changes. And then I'll store that out to my total variable out of memory, so that will update to the value 1. Now I'm going to increment my index into that array, so I'll load in the I variable. At the moment, obviously that's pointing to address 12, so that one there. I then want to increment that one to the next value, so that will go to 13, and I'll write that out to memory. You can see that's now updated. Next we have our new store instruction, so our 2 operand store instruction. So we'll store the immediate value 4 to the high nibble of the high byte, our opcode, and we'll store whatever is in the accumulator to the low byte, and the address we'll be storing it to is defined by the label loop. So what it will do is it'll overwrite this load instruction. It will change that address field within that load instruction. So that instruction there is at address 5, so you can see load, and its previous value was the value 12. So after I've executed that new store instruction, it will store the value 13 to the low byte, and to the high nibble of the high byte, the immediate value 4, which is the opcode for load. So we'll rewrite that load instruction, updating the address it will read. So after that one there, you can see now it will read address 13, and address 13 is the next element in our array. We then need to check to see whether we've read all the elements of our array. So we read in the address of the first element of the array in variable m, so which is the value 12. We then add 4 to it to generate the end address, address 16. So that's obviously address 12, 13, 14, 15. So if I am pointing to address 16, then I've gone outside the array, and obviously I want to stop. So to implement that test, I need an if statement. And as we saw in the lab, if I want to do that one, I would typically do that one with a subtract instruction combined with a conditional jump. So in the accumulator at the moment, I have the end address. If I subtract from that the current pointer, if it produces a 0 result, I know those two variables are the same. Obviously, if I have the variable m minus the variable I, if it gives a result of 0 when I do a subtraction, then they must be the same. So that's what I'll do next. I will subtract that one from it. Obviously, at the moment, they're not the same. At the moment, the variable I at the bottom here has the value 13. So that obviously gives me a non-zero result of the value 3. Then I get to my conditional jump instruction, says jump if 0. Well, it's not 0, so that jump is not taken. And then I get to my unconditional jump, which will loop back to the address at address 5. And that's what happens there. So you can see I update the program counter to address 5, so I'll keep going around this loop until the two variables are the same. And now, obviously, I have modified this load instruction. Previously, remember, it was a load address 12. It was pointing to, obviously, the first element of that array in variable A. But I've modified it now, so it points to the second element of that array. So now I can implement that for loop. I have a mechanism that allows me to adjust at runtime the address that I will read with my load instruction. And just to emphasize, we will be doing this the proper way in the simple CPU version 1D. We will be using register indirect addressing modes, which we'll come to later. Finally, in the lab script, we have a look at macros and how they can be used to help reduce the amount of code you need to write. And we start to introduce the idea of a subroutine. So a piece of software that can be written once and called from multiple places within your program, as illustrated by this diagram. So here we have our program jumping to the same start address. So obviously, the start of our subroutine, our start of our function, is always located in the same location. But where we return back to within our main program will vary depending on where we called it from. So in this example here, we're calling the function at this location in the main program. So we'll jump to the address of the subroutine, execute the subroutine, and we want to return back to the instruction underneath the calling instruction. And then later on in the same program, we'll call that subroutine again, and we'll jump to the same starting location, execute it, but now we want to return back to this instruction underneath the second call instruction here. So how do we do that one in our program? So again, in the simple CPU version 1A, we're going to use self-modifying code. We can use a wheeler jump as described in the lecture. Again, just really to emphasize those ideas about what an instruction is and how it is represented within our memory. Obviously, again, we're going to replace this technique that uses self-modifying code in our final processor, the simple CPU version 1D, and we're going to implement a call and return stack, as you would see in a typical processor. But again, as we will see, adding more addressing modes and adding more instructions do come with a hardware cost, and we'll see that in later lectures. Finally, in this week's exercise sheet, we'll be looking at how we represent small and large values. So how do I represent fractional values? So 1.23, for example. And one way of doing that one is through fixed point representations, which is simply an extension of our normal binary representation. So have a look through that one and make sure you're happy about how fixed point numbers are represented, and do the calculations at the bottom here to prove that it's just the same, nothing has changed. Then we'll have a look at how we can perform calculations that use more than 8 bits. So how can I execute a program on the simple CPU version 1A that will calculate a 14-bit result when I've only got an 8-bit accumulator and adder? Again, we'll consider how we can improve the operation of that code by adding some more instructions. So a new add instruction that combines the previous carry generated by the previous add instruction, and how that will modify the hardware. So what you'll see is that adding these new instructions will significantly reduce the amount of code that you need to write, and obviously that will improve the processing performance of our system. Again, as mentioned last week, if you're not planning to build a robot cockroach in the summer activities, then you may skip this next section where we look at improving its behaviors, but do have a look at the end section here when we're looking at the open assessment preparation. So as mentioned last week, at the end of each exercise sheet, we'll be looking at a modified version of the example exam. So in the example exam, obviously we're using the simple CPU version 1D, and obviously we haven't got to that one yet. So at the end of each of these exercise sheets, I will rephrase one of the questions in simple CPU version 1A syntax. So that's what I've done here. So this week, have a go at question 1. So you're executing the same algorithm as specified in the example exam, with just a few little changes to suit the simple CPU version 1A. And you should only need to write a program using 11 instructions. So it's quite a small program. So have a think about it. It's exactly the same kind of process as you went through in this week's lab. And fingers crossed, touch wood, it should be relatively easy. If it's not, do give me a shout. Always happy to chat. And I think that's where I'll leave it there, and I'll talk to you next week.